I appreciate it a lot. And I want to thank Mike for putting my name in front of the board. Otherwise, there's not have a opportunity. So, as Bonnie said, I work for New Vision for Public Schools, and I work as part of a project called Accessing Algebra Through Inquiry, or A2I for short, but I won't use that today. The point of our project is to support shift how teachers collaborate with each other within schools. So we have a lot of schools in New York in which there is a teacher who is teaching a single subject, the only person teaching that subject, and they virtually never collaborate around their practice with other teachers in the same building. One of the sort of deficits of the small school movement, which is not often talked about, is it makes, you guys are familiar with the small school movement in New York? Move these big, gigantic, monolithic high schools into sort of smaller schools with the intention of sort of focusing more support on students. A deficit, of course, is that it means that you have fewer teachers of any particular subject within each of these schools. And sometimes you have 8 schools within the same building, and those schools actually mostly don't interact with each other except at the administrative level. So you have a whole bunch of people who are still teaching the same number of kids in the same school, but the reorganization of the school structure means they don't work with each other. So our project is sort of designed to try to build more connections and collaboration opportunities between groups of teachers. And we want these teachers, when they're collaborating, to have particular kinds of conversations that center on the mathematical content that they're teaching, to the students that they're teaching it, in the ways that they're going to teach, actually do the enactment of the teaching. So the theory there is that in order to do that, they have to have something in common to talk about. They have to be using evidence of some kind, as opposed to sort of like, well, we're teaching these kids and they just don't get it. I guess we're stuck. Consequence of that is you can't move forward. So introducing evidence into the situation is very important. So my job is to support teachers in having more evidence to use to talk about a la formative assessment. So the connection there is that my work supports teachers in both long-range formative assessment, sort of mid-range, day-to-day formative assessment, and ideally responsive teaching, so formative assessment in the moment. So what I'm going to talk about today are, from my perspective as a practitioner, somebody who's taught for many years and has worked with teachers for now 8 years and supporting their practice, what do they need to know in order to be able to use this thing that we call formative assessment? And I'm going to try to focus on sort of the hard part, which we find is actually the responsive teaching. So it's relatively straightforward and easy to get teachers to use a test of some kind in a formative way as well as a summative way, to sort of make decisions about how to teach the next unit based on the data that they got from the last test. It has been tremendously challenging to get teachers to respond to what students are doing in the moment and make shifts in their practice at that time. So very hard challenge. The 3 sort of layers of my talk are going to start with the mathematical content and the different ways of describing it, followed by the sort of complexity of teaching as a decision-making process, and then offer a potential solution to both those challenges. So first, we're going to do some abstracting for a second. Imagine this ellipse represents all of K-12 mathematics and all the ways it could be known, including some of the ways that maybe somebody might describe as incorrect. And this circle here represents the way teachers know the mathematics. So the first observation you may have is that there are gaps in teacher knowledge. So we're well aware of that. The teachers get to teach K-12 mathematics and they don't know all of it. And there are actually sort of abstractly some areas where they see connections, broad connections between different subject areas, and some areas that feel totally separate to them. And one consequence of that, I think sometimes, is when teachers have gaps in content knowledge and they don't know what the mathematics is, that they sort of rely on tricks to support students in being able to do the steps. This image comes from Nick's the Tricks. It's one of Phil Darrow's favorite things to discuss, sort of like the thing that got Jason Zimba off the fence and deciding to write the Common Core was this image. An image of students having to sort of do some mechanical operations that make no sense without the content. Where do these fraction operations come from? Why is that 15? They're drawing a little cute butterfly. You see a butterfly? So this is sort of like, it's in this ellipse. This this thing that I showed here, is in the ellipse. So it's something that exists as in a way of defining this mathematical knowledge. So who is familiar with Deborah Ball? Great. So Deborah Ball has got a sort of way of categorizing different mathematical knowledge, which I find very helpful. The subject matter knowledge versus the pedagogical knowledge. She sort of builds on Lee Schumann's work of sort of content knowledge versus pedagogical knowledge and sort of describes it in more detail what these things are. I'm not going to really get and define these terms today. I'm going to leave them undefined. But this is what I mean when I say mathematical knowledge is teaching. It's not just the content, it's the ways of presenting the content, it's the ways of understanding it. So just a clarification, there's a great paper that Deborah Ball wrote in 2008. If you want more detail, I would read that. These are my references. One of the things that Deborah Ball did, having made this construct, is test to make sure that it actually makes a difference. So she did a study, 2005, with the objective of trying to figure out, does the amount of mathematical content, mathematics knowledge or teaching teachers have impact student performance? Because if there's no impact on performance or on sort of performance as a metric for learning, then there's no reason to worry about the mathematical knowledge. And it turns out, not surprisingly, that there is a relationship. There is a positive correlation that gets stronger the further on you go in mathematics between the knowledge of the teacher, the ways of presenting the mathematics, and the way that students grow. This graph sort of shows this sort of separated in deciles as opposed to sort of the complete percentile scale. And what we can see is that a teacher who is in the first or second decile has much less of an impact than a teacher who's in the 100th decile in terms of overall understanding of mathematics. But interestingly enough, this is less true for first grade mathematics. The other graph was third grade, this is first grade. So one possibility is that everybody learns first grade mathematics. So trying to figure out who knows it better than someone else might be really challenging for this kind of test. There's still a small positive correlation. Okay, so here's a Common Core math problem that was shared by NBC a couple days ago. You may have seen it on Facebook. There's the old-fashioned way, the new way. The argument, of course, to this person is that the old-fashioned way is far more efficient, so why are we teaching the new way? So given that you're a room full of people who work with teachers, can you take a moment, think about it, and then turn and talk to your neighbors about why we might want students to understand both of these strategies? Why would we want students to know how to do this and know how to do this? And I want your attention, I'm going to raise my hand like this. And if you see my hand raised, you will also raise your hand. And you will do the other thing which is really helpful, which you will try to bring your conversation to a close. So rather than just saying, when I put my hand up, shut up. When I put my hand up, bring your conversation, finish your sentence, and then, so that we have some transition, okay? It doesn't have to be immediate. Okay, so I heard people talking about the fact that this is kind of the mental arithmetic. You might not do this mental arithmetic with these size numbers, but if you want to teach the strategy, it might be useful, this is a theory, it might be useful to start with smaller numbers as opposed to gigantic numbers. Also, my friend pointed out, it's also possible you might want to give students gigantic numbers to point out that it's useful to learn the strategy, right? So they don't go, well, it's obviously 20. Right? I know my place value, it's obviously 20. Of course, the advantage to this way of doing it is that it's efficient. So that if you are stuck in a desert island without a calculator, you can still get the answer. Okay, so the other point I want to make is that there's another type of knowledge that was described in that original chart, which is the knowledge students have of mathematics. And we'll notice that this knowledge students have of mathematics, again, this is abstract, please don't blame me if it's not perfect, that the knowledge sometimes overlaps, is sometimes completely distinct from the teacher knowledge, but sometimes completely contained with what the teacher knows. So you have all these sort of ways students understand mathematical ideas, some of which the teacher thinks are wrong, some of which the teacher thinks are partially correct, and some of which the teacher doesn't know, the student doesn't understand all the mathematics in the way that they understand it. Because it's very rare for someone who's a just learning mathematics to have a circle that is exactly the same. And it's less, right? Pretty clear emphasis of this abstraction is that they know less knowledge in mathematics than their teachers do. So consequently, teachers are important. This is my own slide that really, I think, emphasizes formative assessment as a process. If I want to figure out what to teach and how to teach it, I want to anticipate what my students understand. I want to sort of like, oh, well, they're probably going to do this, they're going to think this way, and so I need to support them in this way. So I need to know, I need to be able to predict how they know the mathematics now, so that I can do that anticipation to make my lesson a better, more useful representation of their knowledge. And then when I'm responding to the ways they actually do the mathematics, I need to understand it in the way that they understand it so my explanation matches what they're thinking. Or my response, which maybe isn't always an explanation, represents and is responsive to what they're thinking. And then when I reflect on what they did and make a decision to revise what I'm going to do next time, again, I have to have it be in response to the ways the students understand the mathematics. And to recognize that the picture is usually muddy and unclear. Because we don't get to see learning, we get to see performance. So here's an example drawn from a book by Elizabeth Green called Building a Better Teacher. Who has read Building a Better Teacher? So if you've not read Building a Better Teacher, I would recommend writing a little note for yourself at some point in the future to read this book when you have time. So, I have a list of references at the end.
Opening section this year in Boston.
Yes. So, if I mention some resource or some study, at the end of the presentation, I have a link to all of my references, the slides, etc. So, yes, it's useful to write things down to remind yourself, but also don't worry if you miss something. Okay, we'll get it later. So, a student writes this. They wrote this thing. So the question might be, who is most likely to be able to diagnose this thinking and understand where it comes from? And I'm going to sort of modify Elizabeth Green's version of this. Is it Hyman Bass, a respected research mathematician who's been working for many, many years in the field of algebra, or is it Magdalene Lampert, who does not have a mathematics degree, but instead has been spending the last 40 years studying the teaching, and in particular teaching fifth graders, which is when this problem would occur. So of these two people, who is most likely to know why the kid wrote that thing?
Probably Madeline.
What's that?
Probably Madeline.
Probably Magdalene. That's a bit of a rhetorical question. So now, why don't we take a moment for...
Bass has been studying teaching for the last 20 years.
I set you up. Okay, so, sorry, I should probably clarify. Hyman Bass works with Deborah Ball at the University of Michigan. He has also been studying teaching for a long time, but he's not taught. So he's maybe 20 years he's been trying to study teaching from a mathematician's perspective. I didn't do that very well. Anyway, so I want you guys to take a moment and just think about why a student would write this. What's your prediction? What's your analysis of why a student might write this thing, this statement, and think that it's true? So just take a second and think about that with each other. Okay. Yeah. Would you mind describing your approach? I was listening.
Yeah.
Okay. Apparently, and I had a student, a fairly good student in a pre-service course for elementary teachers in the fall semester, have a difficulty with a problem exactly like this one. Apparently, 7/12, of course, is 7 parts out of 12 equal parts, but apparently the student flipped the roles and thought of it as 12 parts out of 7 equal parts. So they did it, and they thought 12 was more than 7. So there was a quotient of 1 coming there. And that 0.5, I would think, would be ascertained from 5, a remainder of 5. So they're thinking of it as 1 and 5/7.
Great. Have I represented your... So, again, if I tell the student, if I know the mathematics, I can say, well, that's wrong. Right? Anyone who knows the mathematics of fraction knows that that's not That's not an equal relationship. But if I know the mathematics of children, now I can think about what I would do to support that child. Sure, I think not quite the same thing. So another area of mathematics, and I got to tell you that we have teachers that know a lot of mathematics in our project. We have teachers who know a fair bit of the way students understand mathematics, who do not know the connections between different areas of mathematics very well. So they don't see geometry as representing algebra, and they don't see algebra as being a symbolic way of representing geometry. They do not see the connection between those two areas very strongly. They tend to think of mathematics as being more discrete from each other, this topic and that topic. So a consequence of that, it's very hard for them to think about the broad themes. We know that if students forget the fact but know the broad theme, it makes it easier for them to recall the fact, because they sort of piece it into their understanding of the mathematics. But if they're not taught the broad themes because the teacher doesn't know the broad themes, then it makes it much harder for them to remember all the pieces. They tend to sort of lose track of the overall picture. I think that in part, at least in New York City, this may be a consequence of the over-specialization of teaching. So you have people, for example, who've only ever taught Algebra 1, who actually will say out loud, I don't actually know what the middle school mathematics is. I mean, I might be able to solve problems that are in middle school mathematics, but I don't know what's taught in middle school mathematics. And I don't know what's taught in geometry the very next year. So they're sort of isolated to this area. So it's not, I think that these connections and the understanding of mathematics build up over time, but the systems we use to support teachers in understanding vertical connections, I think are really powerful when they occur. Just an anecdotal experience, I worked in a school where I was required to teach 6 courses. Grade 6, grade 7, grade 8, grade 9, grade 10, grade 11, grade 12. So 2 things happened as a consequence of that. The school said, it's crazy to expect you to prepare all of that yourself. So we are going to have the infrastructure available so you know, day to day, roughly what you're trying to do. And you might need to make some specifications on that, but we're not going to leave you out in the dark with no curriculum, no support. And the other consequence is I worked with someone on those grades. We had everybody teaching 6th grade, everybody teaching 7th grade. Not quite everybody, let's say 3 other teachers in our 4th grade thing. So the difficulty for me was reduced by these 2 factors, but a really helpful consequence is I get to see the broad range of mathematical ideas from grade 6 to grade 12. I know where I'm trying to go to, and I know where they came from. Who is familiar with Richard Skemp's article on instrumental versus relational knowledge? Okay, so another thing to look up. Richard Skemp describes this idea of knowledge as being in, let's say, a park. Let's imagine that mathematical knowledge is a park. And if I'm teaching entirely instrumentally, I'm telling kids how to get to specific spots in the park. But it's almost like I lead them blindfolded to the spot and say, here we go, here you are. Yay, here's this spot in the park. And then I take you to some other spot. Here you are, you're in this spot in the park. And it's very difficult if your eyes are blindfolded between the different areas of the park to know what the park looks like. Imagine being transplanted into Central Park in a much different location. You'd never know how to get from place to place. Relational knowledge, on the other hand, deliberately tries to, if you're teaching for relational knowledge, you deliberately try to build connections between the different areas. Now, Richard Skemp described this, I think, as somewhat a dichotomy. There's instrumental knowledge over here and relational knowledge over here. Whereas I hope that this diagram describes that if you have instrumental knowledge, which is super important, because you can't build connections without knowing things, that there might be some range in between them. So there's hope that even if someone knows the mathematics in an instrumental way, you can help them build connections, be able to see it in a more relational. And to know that these nodes are important. This is a super important node, isn't it? If you don't know that thing, you're going to have it really hard keeping the structure together. The other piece of connections is this idea of hierarchies of knowledge, which I think to some degree are based on how we develop the ideas ourselves as a species, as opposed to how they are logically connected always. But if I'm a student and I want to get to exponentiation, understand exponentiation, I need to understand ratios of things. And I need to understand multiplication. In order to really understand multiplication, I need to kind of understand it as an array or an area model. It requires being able to add, which requires substitution. So there's these sort of, this is sort of like an abstraction. Please don't run off, but it's sort of based on the learning progression documents that were created just after the Common Core. This is sort of a range of the mathematical ideas. And the reason why I think this is really critical is if you're trying to respond to students, your response might not be teach more exponentiation. It might be let's make sure they understand ratios. Let's teach exponentiation in the context of understanding ratios. Just a clarification point, middle school math, high school math. So here's a super important concept for understanding exponentiation, which mostly doesn't appear in the high school standards. Here's another idea, which is that when Magdalene Lampert taught, this is from her book, Teaching Problems and the Problems of Teaching, when she taught, she tended to try to think of mathematics as being a mathematical landscape, and that she really wanted to come back to the ideas over and over and over and over and over again. So she used contextual problems, not because the context was the critical thing, but because it highlighted mathematical features that were, a broad range. So, will you first take a minute or so and just try to figure out A and B of this problem? How would you draw a diagram to show where this car is going? And then talk to your partners about C and D. Is that okay? So just try out A and B yourself, about a minute. All right. I'm not going to claim that this is the right answer, but how many people have something that looks kind of like this? Right? You have some sort of, who does not have this? That'd be great. Who does not have this kind of representation? How are you thinking about it? You have a bar model, so you've made, instead of a number line, you made a box. But you're still having a linearity to your results. Who has something totally different than either a bar model or, what are you thinking?
I had a bar model, but I chopped off the last 1/12 of it.
So you were thinking my bar is out of 60, because that's a nice number. Very interesting. Okay, I like that. Who else has got? Yeah.
Well, I was thinking of a graph, an XY graph. Distance, distance vertical, time on the horizontal, and just draw a straight line, going up and marking off the time.
So there's a deep connection in this problem to both linear functions, 9th grade standard, and 5th grade standard, understanding that numbers exist on a number line. Anything else? You want to add something? Okay. So this is sort of the representation that Magdalene drew to help the students understand their ideas. And it turns out that she didn't just choose this arbitrarily. She did what I did, which is she walked around to see what people wrote, to see is this the right representation to push for mathematical thinking. Bar lines are really powerful because they are sort of automatically extending an idea, which is that there are numbers in between the numbers that we're showing as reference, as opposed to just like putting a series of dots. Right? Does that make sense? So it helps people understand numbers and fractions, for example. This is called a double bar graph, which actually I never got to use because I didn't go for it. So here's another mathematical idea represented in a bunch of different ways. Can you guys work with each other? Just try to take a stab. What is this person trying to represent? Talk to each other. What is this person trying to represent? So what are some theories? What is this person trying to represent?
Distance from 4.
Distance from 4. Very interesting, yes. That seems reasonable. What other things? Subtraction of integers. Great. What else?
I mean, I was looking at how many negative 3s
How many negative 3s?
above the top.
Oh, I see. So thinking of the numbers in pieces. Yeah, that's interesting. Yes.
Adding and subtracting positive and negatively signed numbers.
Okay, great. I agree. Anything else?
Of course, modeling the problem with the blue and the red chips, which is a powerful.
Right, so making sure that we represent the problem in different ways. Yeah, want to add something?
The justification of why subtracting a negative is effectively adding.
So I am the person who represented, these are my representations, and these are a consequence of a conversation I had with my wife a year ago. She said, my son came out and asked, tried to teach me that 4 take away -3 is 7. And I did not understand. And I want to go back and be able to enter that conversation at a different level so that I feel less ignorant of what my son who is 7 knows. So then I went through, I don't think this is quite the order that I used. I think actually I tried to sort of explain what he was trying to do, which was to think that if I want to take away -3 from 4, I need to first have a -3 to take away. That's the way that he really appreciated it. But then I tried to go through different ways of understanding it so that she would eventually latch onto something that helped her. She wanted me to explain how to solve this problem and use a model that she could then understand why this model worked. It took 5 different models before we found something that really helped her understand subtracting negative numbers. So I propose that if you're going to teach mathematics, you should know not just this. Where is it? This. You need to know more than that fact to be able to teach mathematics. You need to know these different ideas. And to know that number lines is so potentially super powerful for introducing and talking about fractions as numbers. I think it's a 3rd grade standard now, I recall. Okay, so now we've got the connections, we've got teacher knowledge, student knowledge, connections between the knowledge. The picture's starting to get really messy. Let's add mathematical language. So if I want my students to be able to leave my classroom and talk to other people about mathematics, they need to know the language that other people would use to describe the mathematical ideas. They need to be able to talk in the academic language of mathematics. That's very important. So we're going to highlight another issue. Try to solve this problem for me. Go ahead. Take a couple minutes. Try to solve this problem. I don't hear anybody. What's the matter? Well, does no one here know Klingon? This isn't Klingon. Don't you know Klingon?
Yeah, but it's not funny.
If you have a student who comes from a Cyrillic language background, new to the country, or I would say most of Asia, I guess, uses different character sets. If you have a student who's coming to your classroom and doesn't know the character set, this is what this looks like to them. This is their experience. They're as completely hopelessly lost as you are. And it doesn't get much better when we translate this into the original text. This is actually not the original, by the way. This is translated from Greek, ancient Greek. This is the original text. Who is familiar with this problem? It's still challenging to solve. If you haven't solved this before, it's still not straightforward to solve. And unpacking the language required to understand this is non-trivial, even for native English speakers. I'm not going to give you time to solve this problem. I am going to give you time to solve this problem. Please take half of the keys that I have and give 2 of them to him and leave 4 of them for her. What I want you to do is to maybe speak that out loud to yourself just to hear what it sounds like, and imagine what an ELL student might experience when they hear something like this. No serious academic language, but maybe there's some issues. Think about this. How might an ELL student new to the country struggle with this sentence? Go ahead, talk. So, if your primary way of sharing the mathematics is orally, right? Imagine there's no text. If your primary way of sharing the mathematics is orally, in this problem, what might a student struggle with?
Well, there's a lot of words that sound the same.
So a lot of very similar sounding words.
Yeah.
If you miss the word that sounds the same as the other word, boy, that's tough. What else?
And the prepositions are also an issue in another language. So give 2 of them to him before the for her, and for, of course, and two and
Who's
two.
getting the P's if you don't know what to means? Is that what you're trying to say? Like, how do we know what's being transferred if we don't know this word and what it means? Other issues.
And the word leave as well is leave can mean what remains, but that would be challenging for many native speakers, I would say.
So the theory I have here is that one common way of supporting students with language is to sort of give them keywords that they can recognize within the language. Again, that's like the instrumental knowledge. You need keywords in order to build up relational knowledge, which is that this is a sentence and the words together have meaning. And if you only know the word leave in the context of remainders, then this might be challenging. Someone else I heard mention that there's no question. Right? There's no actual question here. This is what we call a problem stem. The question is left to the reader. They have to sort of develop the question. That's not a bad strategy to help develop questions with problem stems. But it's worth noting that you should at some point make whatever it is they're supposed to do explicit. Anyway, so, and I like that there's no long, super complicated words in here, but it really highlights this issue. So then, of course, the other issue of mathematics is the mathematical symbols. So aside from the language used to describe it, there's a plethora of different mathematical symbols. And mathematicians, I think, tend to sort of emphasize density of concepts over clarity of ideas. So the objective is to write as complicated an idea as they can in as minimal language as they can. Because they know a lot of them know the complicated idea really well. So they don't want to write out the complicated idea. Like think of summation symbol. Is that up here? I don't see it. Sigma, yeah, there's a sigma. Oh. Think about how complicated it is to write out this statement if you're not using the sigma notation. It's gigantic. It's huge. So they started using mathematical symbols over time to reduce the amount of writing that they had to do. It turns out that this has had huge problems for our transition to digital computers. Because all of these symbols, they don't appear on your typewriter. Right? They're not on your keypad. Anyway, so symbols are a problem. And I propose that this is the very first symbol that actually kids struggle with. Right? They have hundreds of, maybe even thousands of experiences where this symbol means find the answer. 4 plus 6 equals blank. Over and over and over again, they're told to find the answer. They think that this symbol, by the time they get to middle school, and often high school, means makes. Regardless of whether somebody at one point said, this is what it means. It means that the two sides are equal. They learn the language both from what we say that it means and how we use it. Those are two sort of competing interests. Here is an example from my college textbook when I was doing abstract algebra. Just sort of look at that for a second and think about the language requirements by the time they get to university math. This is the end. This is a course that normally would appear in your 3rd or 4th year of university mathematics. The assumption is that you know some of these things. One very common approach I have seen in mathematics textbooks is that they pick some symbol that they want everybody to know, and they either put it in the back of the book, or they put it in the middle of the text somewhere when they're introducing the idea. One time they introduce the symbol to remind people what it is. And so consequently, you have to spend a lot of time when you're reading this language going back to remind yourself, what do these things mean? That increases your cognitive load and makes it very difficult to understand the ideas. So, broad ideas. The mathematical ideas, the teachers need to know the mathematical ideas in some way, including the way students understand it, including the connections, including the language, including the symbols. I'm hoping, I showed this to my colleagues, and I said, does this look really messy? That's my intention. It should look really messy. This is a complicated thing that the teachers need to know. And teacher educators, ourselves, also need to know these if we're going to support teachers. Okay, so that's the end of the mathematical knowledge that teachers need to know. There are a lot of other things that are non-mathematical knowledge they need to know. For example, they need to understand that there's social status in classrooms. And someone might not speak up. They might not want to talk because they feel uncomfortable. They need to understand that the singles and who they call to ask, etc., teaches kids, in the same way the use of symbols teaches kids what it means to be a mathematician. So if your classroom is only ever the 5 fastest kids who get to respond, the kids learn that being a good mathematician is about being fast. If it's only ever the boys or only ever the girls who get to talk, that has a consequence in your classroom. There are a variety of other what I'll call non-mathematical ideas in that genre. I'm not an expert in that area. I recommend reading a lot of Warren's book on strength in numbers. She unpacks some of those ideas quite nicely. So, teaching is really about the next part. Teaching is teaching decision. If I'm a teacher, I make lots and lots of decisions. Lots of decisions. And it turns out that actually in a typical day, a teacher might make as many as 1,500 decisions that impact student learning on a regular basis during the day. This does not include the planning the night before or the response afterwards. So that too feels like a lot of different decisions. That seems kind of complicated. It gets worse. These researchers said, well, at every decision there are choices that could be made. So then they tried to calculate what are the number of choices that I could be making when I'm teaching. I mean, I can always choose to stop talking and do something different. Right? I can always choose to do that. I can always choose to ask that student or that student. So this is the sort of size, rough size of the decision space. These are the number of choices every time a teacher makes a decision. I'm going to say that this number, I would run off and say, David Weiss says the number of choices is 4.23 times 10 to the 28. Let's think about just the scale. This is a very large number, right? This is a very large number. Rather than saying that there's some concrete evidence. There is did I link it here? It's in my references. There is actual, believe it or not, research on this. Okay.
Bigger than a mole.
What's that?
It's bigger than a mole.
A lot, yes. It's larger than the number of X that people know about, right? Where X is something that could be known about, aside from this thing, decisions. So then, teaching becomes the choice of which branch am I going to take, and there are a lot of branches, and so if we just do the math, we see that there are 1,500 to the 4.23 times 10 to the 28 different ways my math classroom can occur on any given day. That's just per day. So not even per teacher, etc. There are a lot of different ways that a classroom can occur. So teaching is highly complex. I would propose that there are some ways that people think about reducing that complexity. One of them is to use the protocol that I'm using now, which is, do I continue talking? Yes, no. I have now a smaller decision space to make. What do I talk about? Well, I plan that in advance. That's not happening right now. I'm thinking about this in advance. So when we see teachers making decisions we don't understand, we should recognize that the complexity of making decisions is actually huge. So then I want to talk about a way to reduce the complexity. And I'm going to talk about the work of Magdalene Lampert. There is a really nice article that describes this in lots of detail. That's why I have this reference here on the slide. You don't obviously have time to write down this reference, but it's in the slides. It's in the link at the end. She went to this Italian language school. Let me back up. She was sick of her job because she was really struggling to make any success. She did not know how to support teachers in the kind of teaching that she was doing. So she took a sabbatical, and she went off and she went to an Italian language school just to take a break. She wanted to be in Italy for a while, learn about Italy, just relax. And so she signed up for language classes. And she was in this class, and the very first day, she noticed something kind of strange. Two important things that were to her like different. The first was that the teacher was actively walking around trying to figure out what everybody understood about Italian so far on the first day of instruction. The second thing was that about halfway through the class, the teacher looked at his notes, okay, left the classroom for 1 minute. These are all adults, so this is maybe not what you would do in an elementary school. Left and came back with a different activity and said, okay, we're going to stop this activity. This is not working. I have a different activity because I've noticed X. And so they did a different activity afterwards. So what she noticed was first that this teacher knew how to do this. Knew how to look at the learning or the performance, that was occurring and make a decision based on that performance. What are these students able to do? I'm going to make a different decision as a result of that. Second, it took them 1 minute to go find the resource that they needed. So this suggested to her that the teachers needed infrastructure. They needed support and resources aligned to the ways that we want them to teach. It's not enough to say, teach like this, here's your blank piece of paper. Go. They need some structure. They need to build it up over time so they understand it. The second thing that she noticed when she was in the schools that all of the teachers did this. There were no teachers in the school that were not teaching in this way. Everyone had high quality teaching. So she investigated. She found they all went to the same teacher education school, specifically designed by this Italian language school, totally separate from anything else that was occurring. They had their own teacher education program for the teachers who were teaching in their classes, and that the teachers tended to rotate. So it wasn't just like they had the same set of people all the time. These people changed all the time because they went off and did other things. Teaching in an Italian language school is not financially rewarded. So there's high turnover. So she tried to figure out what one thing they were doing to try to help support them, and she learned that they were using these things they called instructional activities, which are ways of reducing the complexity of teaching. Magdalene and Lamp describes them as, I want to make sure I have the right language. I don't have quite the right language, so I'll make that. She called them designs for classroom interaction. So the idea is not a scripted lesson plan that says what you do from moment to moment, but a structure that suggests strongly things you should be doing to help you make decisions. It focuses on gathering evidence of performance and as a metric for what's being learned during the classroom time. So what I propose is that understanding instructional activities without seeing one is super hard. So I'm going to deviate from the norm from a keynote speaker perspective, and I'm going to teach for a little bit. It's not going to be model teaching. It's going to be teaching that helps us think about the decisions required if you're going to be teaching. I'm going to choose content for this teaching that everyone can access, ideally. And in fact, I would be very surprised if you cannot access this content. And I'm going to use one of these instructional activities somewhat explicitly so that we can think about what it means to be a teacher teaching in such a way that they are developing an understanding of what the students understand. So, in order to do that, you will need a partner, but I think I have managed to condition you to that stage, so it should be okay. You should know the people around you, and I propose that we're going to make some assumptions about this, which is that you already know largely how to talk to each other, which is, I think, something that is not true necessarily for students, or even the teachers that I work with. So you guys are a group that sustains itself over time. You've worked very collegially with other people. I'm going to assume that you talk to each other productively. Our objective in this activity is to think like a mathematician. And mathematicians, I don't want to say that they're lazy, but they like shortcuts that they can justify. They would prefer often to have an elegant solution that is brief than a complex solution that is lengthy. So they would ideally like to do less work. And so they try to think about the way numbers work in order to make decisions about what is a reasonable shortcut to use. We're going to start by sort of looking and interpreting what am I asking you to think about, what am I asking you to work out. Then you're going to talk to each other and consider that structure. Then we're going to talk as a group to sort of like see what happens. And then you're going to get a chance to reflect on learning. What's the big idea that we're trying to take away from this activity? Does that make sense? So you are students for a little while, even though I know all of you know this mathematics. There's a tendency to sort of shortcut, let's say, which is to look at the question and try to answer it. Blam, I know the answer. Our objective is not to answer the question, although that will be a consequence of our work. Our objective is to try to find a shortcut to make finding the answer easier. Okay, that's an important difference. So what I'm going to do is I'm going to show you the problem, and I'm going to ask you to pay attention to it and just to see what you notice about it. Are there any questions about that? Great. Okay, so what do you remember what you noticed from that problem? Talk to each other. What did you notice about that problem? I'm going to give you another chance to look at it. Another chance to look at it. We'll talk why I did it this way later, but I'm going to give you another chance to look at it. Okay. Now, what did you notice about the problem? Let's try again. I thought I had everybody, but I did not. Okay, we're going to try again. I'm going to show it to you very briefly. Okay, what did you notice about the problem? Okay, let's hear some of these noticings. Again, things we noticed about the problem. Let's hear. Would you like to share something?
Oh, I've got, the obvious is it's all addition and subtraction, and some of them are positive and negative.
Okay, so all addition, subtraction, and some of them are positive and negative. Those two ideas are connected to each other. Yes?
All multiples of 9.
All multiples of 9. What else is somebody? Yes?
No parentheses.
No parentheses given.
No equal sign.
No equal sign given. Great.
Well, I got lost in trying to do a strategy, and I was thinking I would have to try to combine numbers to make them, so I only saw that the left half initially, and I was thinking I need to make benchmark numbers so I could get them to add the chunk.
So some of the digits of the separate integers there was 9.
Oh, interesting. What else do people notice?
We get that maybe a 0, representation of 0. If it doesn't, there's no equal, and it's all adds to nothing.
Maybe it adds to nothing. Okay, so this is an inference on based on what you looked at. Okay, what I want you to do is to use one of these things we noticed. I'm going to write them down. Use one of these things we noticed to determine the value of the expression quickly in your head. No pencils. Okay, try to figure out the value of the expression in your head. I'm going to write down the things that you will notice.
Well, the sum of the digits in general.
Not just this, that's not the digits.
Right.
Great. Okay, so does everyone have a strategy they can use? I unfortunately had to write that stuff down, which means I did not do what I had planned to do, which is to walk around and hear. So I don't know who I should ask. Literally, I have no idea. But this woman seems really eager.
Well, they're all multiple of 9, so factor out the 9, and what do you get? You get 9 minus 8, which is 1, plus 7 minus 6, which is 1, plus another 1, plus another 1, so that's 5, times 9 is 45.
Okay, so just clarifying, you said I'm going to change this to When you say factor, I mean with parentheses. Right. And then you said that this is 9 minus 8. Yes? And then plus 7. I didn't hear you say all these things, that's why I'm pausing. Plus 5 minus 4. I'm going to run out of space. Plus 4. Minus 4 plus 3 minus 2 plus 1. Is that right? And then n parentheses. And then you said that you knew that was 45. How did you know that?
Well, 9 minus 8 is 1, 7 minus 6 is 1, 5
So then-
minus 4 is 1.
You looked at these two and you said these are 1. You grouped these two, yes?
Yeah.
Great. And then you added the ones together, and then you got 9 times 5. That's great. 45. What's another strategy somebody used? Something different. Yes, sir.
I went from right to left.
Right to left.
Negative 18 plus 9 is negative 9.
So
Negative
you
36
said-
plus 27 is negative 9.
Hang on, let me get this down. 36, 45,
It's just easier. Seems easier.
72, minus plus. Oh, I got an error.
It's 27.
Okay, so you said these two are minus 9.
And then the next two are minus 9. And the next two are minus 9. And the next two are minus 9.
Okay.
So it's 81 minus 4 9s or
81 minus 4 9s.
yeah. It's 45.
Which is 45. Another strategy. Yes, ma'am.
So,
I wish I could just press the button and have they go up.
so this is the sandwich method, and so you start left and right, that's positive 90, and then keep working in, negative 72 and negative 18, that's negative 90. Keep working in, you get positive 90, and then, anyway, it all cancels down except for 45, and that's all.
Okay. I was concentrating on this.
I knew it, I knew
Okay, try again.
The outer numbers are positive 90, 81 and 9.
So you're saying that this number, well, do you mind? Okay, well, I'm going to have a trouble here. I'm going to talk briefly, meta aside. I want to represent your thinking with what I write up here so that everyone can understand. So to do that, I was planning on drawing connections between the two numbers. Then I realized that you're probably going to connect the next two numbers as well. It's going to make it hard for me.
Just go up.
What I'm going to do is just make sure I leave myself some space.
Yes, that sounds good.
And you're saying that this is
Positive 90.
positive 90. Okay?
And then keep working in, negative 72 and negative 18. So negative 90.
So this is negative 90. Great. Keep going.
Okay, and then the next two working in are positive 90, right? 63 and 27. And then the next two working in are negative 90. These all totally cancel each other, and you're left with 45.
So you're saying negative 90 plus 90, negative 90 is 0. They cancel each other out, and we're left with 45. Let's get one more, because there's a reason for the one more. Sir, I remember you've talked once.
I see 4 differences that result in 90, and result in 9. So 81 minus 72 is a 9, 63 minus 54 is a 9, 45 minus 36 is a 9, 27 minus 18 is a 9, and if you like symmetry, and I do, I put a minus 0 at the end, and then I've got these 5 9s, and that's 45.
9. 9.
And we're not supposed to evaluate that one of these is better, right? But some of us are doing a lot of
You went minus 0?
Yeah, you could. I mean, I didn't have to, but I like that symmetry when I saw the other things go on.
And then you say that's 5 9.
Yeah. 45.
Okay, I'm going to pause there. So clearly this problem is a lot of ways of solving it.
Yes.
What I want you guys to do is I want you guys to reflect on the similarities between these problems and just write a sentence using one of these 4 prompts. So write a sentence using either A, B, C, or D as your sort of structure to think about what's the big idea that connects all of these solutions that we looked at. And I'm going to number the solutions because I think they might be hard to see otherwise. Let's put them in the order that we heard them. 1, 2, 3. So think about or write a sentence that describes, using one of these prompts, that's thinking at the big idea that you've used, rather than the next time you're given this problem, which will be now, that you're going to solve this problem. The big idea. And when you're ready, share that with your partner. Share that big idea with your partner. I'm going to summarize what I heard the room say. Protocols.
We like to talk.
That's okay. Okay, so I heard a couple of different big ideas come out, actually, which is interesting. One person I overheard talked about the distributive property as being something that sort of came out a couple of times. Somebody else talked about thinking about the multiples of the numbers, and somebody else talked about, I don't think they use this language, but I would call it the associative property, where we're sort of kind of deciding what order we want to do this calculation to make the calculation easier. So all 3 of those, I think, are really productive ways. If we're trying to solve these kind of problems, we really should be thinking about whether we can group the numbers differently. We should be thinking about whether or not we can factor something out of the numbers to make the calculation simpler. And those are sort of big ideas that we can take away the next time we want to calculate something. Okay. So now, pause, and moment of David doing some more interactive teaching than before. What decisions do I have to make in order to do that? What do I need to know in order to be able to make those decisions? Brainstorm with each other. Move into larger groups if you need to. Maybe groups of 4 would be good for this, groups of 4 or 5, with 3 in the back. What decisions did I make? And what do I need to know in order to make those decisions? Let's have some of an open discussion. We've got 9 minutes left, so that I end the right time. Let's have an open discussion about these kinds of things. I heard lots of talking about decision making. I heard lots of talking about content knowledge. Let's try to sort of share some of these ideas to the room. Yes?
Well, one of the things I noticed was giving people, or giving your students the time to play a little bit. I think sometimes we're so driven by, I got to get through this content in this amount of time, that we lose some of the fun stuff. I mean, maybe a simple problem like that could be a lot of fun if you let people engage their minds a little bit, but it takes time.
Got it. So I am balancing time against some other goals of my classroom, right? The time to teach the content versus the time to teach what it feels like to be a mathematician. Maybe one way of describing the fun. Something else?
Well, by viewing this problem, we see that problem solving is a rich and rewarding enterprise in the sense that there are multiple pathways in in order to solve different representations. And I think we always have to keep that in mind.
Okay. Somebody want to add on to that idea?
I
Yes?
think that one of the big ideas that this really lends itself to well is pattern recognition. And that if we can find the time to allow them to see the patterns in the way that they think, we can then make connections between the way that they think and mathematical properties that whatever it is that we want to be highlighting at this point.
I agree. We were discussing that the problem was well pitched as far as like to the people in the group. I mean, there's just, I guess, some assumptions you could make, but I mean, everyone seemed like they were staring at it every time we went back and forth. We were looking at it next month.
Right. So there was something in the structure of the way I presented it that was made you all equals. I knew in advance that some of you are mathematicians, and some of you are not. Some of you are not mathematicians yet. You are, let me amend that. Some of you are people who our society recognizes as mathematicians because you have a particular degree and a particular occupation, and some of you are mathematicians who do not have that certification. So I had to choose a problem that everyone could access, but I had to choose a strategy for introducing it that did not give someone an undue advantage. Yes?
Yeah, and you also have to think about how you introduce that problem. So you flashed it on quickly, but you also, before that, you preluded it by saying mathematicians look for structure. And so, for example, if I were doing something like this with my class of future elementary teachers, it would sort of cut off the, okay, let's just, or at least it would discourage just plain, let's do a subtraction, 81 minus 72 equals, plus 63 equals, minus 54 equals, just doing the deadhead calculation.
Absolutely. I made a mistake, which is worth noting, which is that in this initial one, there's a symbol on here that did not give you enough time to think about, and maybe that symbol should be on this page as well, so that we know that this is not a pencil and paper activity, that we're intended to try to think mentally as opposed to writing out steps, which I know that some people wanted to obviously write down the thing, make it easier to do. The other sort of reason why I'd only flash it for a second is so that you don't have time to see the whole thing. You literally have to look at the structure and then rely on the other things people notice. So I'm now forcing you to be reliant on the rest of the group to support you in trying to solve the problem. And I have done this before where I gave a problem like this, not this problem, but a similar structure, where I gave people a minute to look at it. And the consequence of a minute of looking at it is that most people just solve the problem the way that they've always solved problems. They're not required to think about the structure. What math practice is that, by the way? I'm glad right? This is an activity intended to help students make sense of the structure of mathematical ideas. So the really big idea, aside from whatever structure exists within that content area, is that structure is a thing. Now, I did not write down MP7 anywhere. It's worth noting. So, should some Common Core thing stop being taught in New Jersey, in New York in a year, I think it might still be relevant to think about the structure. And then the reflecting on learning, right? Trying to get you to think about the big ideas. Okay, I'm going to summarize my talk in 1 minute. There is a lot of math stuff people need to know. Lots, in different ways. Teaching is decision making. It can get complex. I did not talk about something called best practices, so if you go and read my script at some point, there's some more detail here that I chose to skip. And that these instructional activities, this one that we saw, contemplate and calculate, has some of these core teaching practices that are objective and to help teachers understand. But these are all a container, the teaching practices, the name of them, whatever, are all containers for supporting decision making. These actually come from the Teaching Works project. Who's familiar with Deborah Ball's Teaching Works? Again, something else to really learn about. This is my contact information. This is the link that you may want to write down if you want to access any of these resources later with the references. So I listed things and people. This is where those are. The other name I could have given for this talk is Other People's Ideas.